way, don't hesitate to stop me and ask questions. Of course, today is an introductory lecture, so everything is more or less kind of evident for you. You know things, but in the next lectures, when I'm going to introduce you case studies with some details, some mathematics. Of course, we have a very informal settings, so you are free to ask me questions whenever you want and clarify things if you don't understand. And you don't have to ask me questions, of course. It's not obligatory at all. You may think about them later. You can ask me questions later when you like. You can write me. We can talk after the lecture. I mean, it's absolutely free setting. Right. So let's carry on. Yeah. There is a lot of mysticism in mathematics, and of course there is a lot of interesting things in mathematics, striking things. As I said, all of a sudden you can see connections between areas which are not connected really from the first point of view. Gödel thought that we can really intuit that mathematical truths sometimes. This sounds like mysticism, isn't it? What it is for him that he sees that the axioms themselves force upon us. So the notion of mathematical intuition is quite a vague notion. This is one thing. Another thing, of course, Plato's ideas of immortal souls and recollections from the previous lives is also quite an extreme mysticism, right? And we probably would like to avoid such strong premises in our philosophical approach to solving the dilemma, let's say. Or maybe, of course, it's not that we are going to solve the dilemma, but at least we would like to have more or less a scientific approach to these issues. Yeah? Kind of a relevant, plausible approach. And nowadays Platonism still exists, but of course without these strong mystical premises, not so much. One of representatives of this stream is James Robert Brown from University of Toronto. He has written very interesting books, at least two of them I would highly recommend. I will give you a reading list later. Laboratory of Mind and Philosophy of Mathematics, where he talks a lot about the use of visualizations and thought experiments in mathematics and science, and he thinks that mathematics is tightly related to physics and science, and he thinks we don't have to lean so much on causal approach of our knowledge that we necessarily will have to a causal interaction with things. We have to see and touch and sort of be in a kind of a causal interaction. It's not necessarily so. And he also has an idea of something like intuition. And he thinks that pictures, visualizations, thought experiments are those kind of intermediates between us and abstract objects. So this is probably how we can come to know mathematical truths. that he thinks that sometimes we look at the picture and we see the idea. Sometimes we look at the diagram and we see the idea. Some pictures are not really pictures, but rather are windows to Plato's heaven. Plato's heaven is the world of ideas. Yeah? As telescopes help the unaided eye to see the stars and planets, so some diagrams are instruments rather than representations, which help the unaided mind's eye. So we have a mind's eye which sees the ideas from the Platonic heaven, and diagrams and thought experiments are kind of instruments which help this. So this is how he answers the epistemological question, how we come to know abstract mathematical objects without causal interaction with them. This is his answer. So at least his approach doesn't rely so much on Plato's immortality or Gödel's mysticism, but he thinks that Platonism is necessary in order to explain why things are right. So he thinks that, why mathematics is true, it's just because those objects, mathematical objects, do exist independently of our mind. That's why mathematics is true. So his point of view is quite an extreme Platonism. This is one thing. And another thing, I personally think, if pictures are instruments, like telescopes, why don't we come to know how these instruments are set up? Why don't we study how they are actually arranged? Why don't we try to explain them? Because these diagrams, which you can find in geometry, analysis and other disciplines, they are so well developed. They are so clever, and they are so efficient. So, which means mathematicians really work hard in order to make them so efficient. And for us philosophers, it could be useful to understand how they work on these visualizations in order to understand the mechanism how we come to know mathematical objects. So this is kind of my research idea, which I think is worth to pursue, and which Brown doesn't really want to develop so much. So the intuitional approach strategy is to have a good range of case studies, have many of them, have these case studies from different levels of complexity, not just simple cases from school mathematics, Euclid. Of course, it's extremely useful to understand what Greeks were doing and how they were doing, of course. But it's good to know more complicated cases, and cases from different domains, not only arithmetic and Euclid geometry, but mathematics. Nowadays, mathematics is so diverse, is so rich, and computational areas are so rich, and mathematics is tightly correlated with sciences, medicine, economics, finances. We have an immense number of instruments, intellectual instruments, which enrich mathematics. So this is what kind of case studies we should study, I think. And I personally think that we have to have more case studies from today's mathematics. What about today's mathematics? What is happening now? Again, it's crucial to know what people have done centuries ago, and ideas of those geniuses are very, very useful to be revised again and again, that's for sure. So I did mention that one of the approaches, one of the strategies of philosophy of mathematical practice is also a historical approach, to look how mathematics has been developing, what's happening, also what's happening with foundations as well and methodology. So yeah, and I put my heart here because yeah, personally I would like to learn more about current mathematics. And my examples will be from current mathematics. This is my promise. I think it's important to have a dialogue between mathematicians and philosophers, to communicate more with mathematicians, not just to say how mathematics should be done, but ask philosophers, ask mathematicians, and maybe mathematicians will come to ask philosophers as well. Paulo Mancoso has written a book, Mathematical Practice, as Philosophy of Mathematical Practice in '96. And he suggests that we have to understand mathematical practice as it is done, not as it should be done. So, yeah, well, I think it's clear what he means. Asking mathematicians what do they think about philosophical questions in mathematics. Of course, there are mathematicians who have no time to think about philosophical issues, and it's not their obligation, actually. It's not really their job, but some of them are interested in these questions, and sometimes they do share their ideas with other people, and they write nice essays. For example, Terence Tao, a mathematician from California, who is working in topology and analysis, has written a paper what a good mathematics is, and he gave a long list of criteria of a good mathematics. He really worked hard on this problem, because probably he's interested in this issue. You know, it's important for them what kind of mathematics he is doing, and whether it's good or bad, and how to improve it. So, but if you look at the list, yes, problem solving, of course, technique, theory, yeah, this is important. But also you can see inside, you know, conceptual simplification, heuristic, analogy. He talks about discovery, straight away, revelation, you know, connection and of areas, application. So mathematics, even if it's pure mathematics, not applied mathematics, still there could be some interesting applications to science, statistics, and other fields. Exposition. It's important that you are able to explain what you're doing. Pedagogy. Yeah. Yeah, I have to tell you that philosophy of mathematical practice also pay attention to the ways how mathematics is taught in schools, at the universities, and unfortunately nowadays there is a big problem about teaching mathematics at school. For example, last year in the UK, the government invested a big amount of money in order to improve school education in mathematics. Well, it's just because children cannot use mathematics after they finish in school, and the idea is maybe we have to make it more interactive, more visual, more interesting, motivate them better. So, and Terry Tao, actually, what he means here, he means that, for example, some areas of mathematics are traditionally taught from combinatorial, algebraic point of view, but in fact, it's also possible, having some, given some geometrical approaches, it's also possible to teach them from the point of view of geometry. And then it could be maybe more efficient, or maybe it's important to introduce both points of view so that the students from the very beginning could have a broader horizon how to look at the objects. So vision, public relation, mathematics foundations, historical relationship, rigorous, yes, that's of course, sure. But also beauty, mathematical beauty, elegance, creativity. Mathematics could be useful, strong, yeah, deep, definitive. So you can see it's not only about proofs. From the point of view of a mathematician, mathematics is not only about proofs. He has a nice blog, Terence Tao. If you Google Terry Tao blog, you can find up-to-date discussions, mathematical discussions, very interesting. You can just Google Terence Tao blog, it's easy to find it. And this is a link to his paper in archives, what a good mathematics is. Timothy Govers is saying, yes, of course, you can find these two paradigms of how people look at mathematics. One is two paradigms. One is that the point of solving problems is to understand mathematics better, so it's understanding paradigm. And the second one, the point of understanding mathematics is to become better able to solve problems. So what he means that some people think that mathematics is about solving problems or proof production, enterprise, right? But he is saying, but actually problems have hidden depths. When you start solving a practical problem, for example, or you find a proof, all of a sudden you bump into an interesting, unpredictable facts about these mathematical constructions. You discover some interesting relations with other areas, and things you don't anticipate at the beginning. And this would be missed by intellectual approach. If you concentrate on proof production, it means that you don't value such things as such depths and such things as understanding mathematics better through proof production. Right? Another great mathematician who unfortunately passed by 2 years ago, William Thurston, anthropologist as well. He has a very interesting paper on proofs and progress in mathematics. You can find it online, also on Terry Tao blog. He is heavily criticizing definition, theorem, proof model of mathematics. So he is saying, no, mathematics is not only about definition, theorem, proof, because the measure of our success is whether what we do enables people to understand and think more clearly and efficiently about mathematics. So this is what mathematicians think. Mathematics is not only about proofs, it's about many things, many other things. Explanation for him is crucial. And you can see he's really sometimes working hard and explaining things. On this photo, he has a node around his neck. You know, there is a node theory in mathematics. It's a part of algebra, very abstract things, but in fact you can explain some things using a rope or laces. And this is what he's doing on this photograph. And he has a very interesting book, Three-Dimensional Geometry and Topology. Three-dimensional geometry is about surfaces, three-dimensional surfaces. So, for example, a ball, football, yeah, is a three-dimensional object, but the surface is two-dimensional, right? And but in mathematics we also have three-dimensional and n-dimensional surfaces. How to imagine these things? How to imagine n-dimensional, at least four-dimensional space? It's very hard to imagine this. And in this book, William Thurston has a very, very interesting explanations and suggestions how you, thought experiments, illustration, how you can actually train your imagination, your perception, your vision of the world, of the space, so that you can try to imagine these old things. I highly recommend. It's kind of technical, but he is very reader friendly, and he works hard to explain these things and make them visible. So here are more names from philosophy of mathematical practice. In fact, 10 years ago, these people organized an association of philosophy of mathematical practice. So they meet, I think they meet every 2 years in order to share their ideas and new research. The recent volume on thought experiments by Van Bendegen is a collection of papers on thought experiments. Jose Ferreiros and from Sevilla and Jeremy Gray, they have a more historical approach to philosophy of mathematical practice, as Paulo Mancoso does. Nick Detlefsen has a project on ideals of proofs, when he develops the connections between the ideal criteria, the criteria of ideal mathematics, ideal mathematical objects, ideal proofs, purity, and connection with science and physics, and philosophy of mathematical practice. Very interesting project. Hannes Leibniz from Munich. He is the founder of Laboratory of Mathematical Philosophy. Laboratory of Mathematical Philosophy. Mathematical philosophy is not philosophy of mathematics. Is something in the spirit of Leibnizian idea that philosophers come together and instead of dispute, they say, let's count. So mathematical philosophy develops instruments, mathematical instruments, to approach some philosophical ideas, philosophical problems. So they work a lot on probability theory. They use probability theory in philosophy. Yeah. Giuseppe Longo, Petito, and Teiser, they have a project on geometry and cognition. So this is more like cognition psychology and philosophy and history of mathematics project. Nelson, very good books about proofs without words, proofs with visualizations. James Robert Brown, as I said, Nets, it's a historical review of Greek geometry, Greek mathematics, and he analyzes how the Greeks were using visualizations, how important it was, and what is the connection between visualization and the argument. Marcus Giaquinto from University College of London is working on visualizations and also mathematical beauty. Ken Manders has a very interesting paper on Descartes, for example, as a case study. So he is pursuing this idea, strong idea that we do have to have case studies in mathematics, from mathematics, and he is showing that if you take proof production enterprise approach, you really miss all the beauty of Descartes' approach to geometry. If you know, Descartes would say, what Descartes has done to Euclid's geometry, he developed an approach, coordinate system, algebraic approach, when you can write down all the bulky geometrical representations. So not always visualizations are efficient in working, in doing mathematics. Yeah, it's not that I'm trying to say that everything has been done with visualization. This is the best way, or geometry. No, it's good to have various instruments and various approaches, and some of them are more efficient for solving some problems. So Descartes simplified, he suggested a much simpler approach to geometrical problems. So all these bulky Euclidean constructions, I mean, if you have three-dimensional objects, one placed into another, and you have to calculate some problems about them. It's hard to draw them, it's hard to see how it's going on in 3 dimensions. You have to draw it on a paper which is 2-dimensional, so the problem may get very, very complex. However, when you write everything in terms of coordinates, yeah, in coordinate system, you write down your equations, and then you apply algebraic technology of solving algebraic equations. You do just simple calculations. However, the proof production enterprise would miss this advance of mathematical thought, right? They wouldn't be able to appreciate this great result in mathematics. So yeah, these are the main names in philosophy of mathematical practice. I kind of gave you an overview, and here is a recap. What we have done today, we looked at the Benasarov dilemma, that it has two epistemic, that it has ontological and epistemic forms. And as I said, ontological is very hard, but maybe we can start with epistemic. And there are two approaches, intellectual and intuitional. I gave you a very brief impressionistic sketch of these approaches with emphasis on philosophy of mathematical practice as a contemporary approach. I gave a list of main research questions which could be